Ever wondered how websites like Amazon or Netflix seem to know exactly what you want? Or how your favorite social media app remembers all your friends and photos instantly? The magic behind it all isn't actually magic, it's data. And today, we're going to pull back the curtain and demystify what they are, how they work, and why they're the unsung heroes of our digital world. So, what exactly is a data? At its simplest, a database is just an organized collection of data. Think of it like a super smart digital filing cabinet. Instead of messy stacks of paper, you have neatly organized information that you can find, update, and manage with incredible speed and efficiency. This filing cabinet is run by something called a database management system, or DBMs. The DBMs is like the super librarian for our digital library. It's the software that lets us talk to the database, ask it questions, and tell it what to do with the data. Now, you might be thinking, can't I just use a spreadsheet for that? And you're not wrong. For small amounts of data, a spreadsheet works just fine. But imagine trying to manage the data for a company like Spotify with hundreds of millions of users, billions of songs, and countless playlists. A spreadsheet would crash and burn in seconds. This is where databases truly shine. They're built to handle massive amounts of data, ensure its integrity, and allow many users to access it all at once without causing chaos. Let's dive into the most common type of database you'll encounter. The relational database. This has been the king of the database world for decades. The idea behind it is simple but powerful. Data is stored in tables, which look a lot like spreadsheets. Each table has rows and columns. For example, in a university database, you might have a student's table. The columns would be things like student ID, first name, last name, and major. Each row would represent a single student. Then you might have another table called courses, with columns for course ID, course name, and professor. Now, here's where the relational part comes in. How do we know which students are in which courses? We create another table, maybe called enrollments, that links them together. This table would have a student ID column and a course ID column. By linking these tables using these unique IDs called keys, we can create powerful relationships. We can honestly ask questions like, show me all the courses that Sarah Smith is taking, or which professor teaches the most students. This structured approach, known as a schema, is what makes relational databases so reliable and organized. The language we use to talk to these databases is called SQL, which stands for Structured Query Language. It's the universal language for asking databases for information. But the world of data is always evolving, and so are databases. In recent years, a new kid on the block has been gaining a lot of attention. NoSQL databases. The name is a bit misleading. It doesn't mean no SQL at all, but more like not only SQL, these databases were born out of the needs of modern web applications, think Google, Facebook, and Amazon. They needed to handle enormous, unstructured, and rapidly changing data that didn't fit neatly into the rigid tables of a relational database. Unlike the strict schema of relational databases, NoSQL databases are much more flexible. There are several different types. One is the documented database, where data is stored in flexible JSON-like documents. Imagine a file for each user on a social media site. One user might list their job and city, while another might list their hobbies and favorite movies. A document database handles this variety with ease. Another type is the key value store, which is the simplest of all. It's like a giant two-column dictionary. You have a unique key, like user 123, and a value, which could be anything, a name, a profile picture, or even a whole block of text. They are incredibly fast for looking up data when you know the key. Then there are column family stores, which are great for analytics on massive datasets, and graph databases, which are perfect for understanding relationships. Think of a social network. A graph database stores users as nodes and their friendships as edges. This makes it incredibly easy and fast to answer questions like, find all the friends of my friends who live in New York. Trying to do that in a relational database with millions of users can be incredibly slow. So, how do you choose? Relational or NoSQL? It's not about which one is better overall, but which one is right for the job. If your data is structured, consistency is critical, and your requirements are well-defined, like for a banking system or an e-commerce store. S Inventory a relational database. Using SQL is often the best choice. It's reliable, mature, and ensures data integrity. You don't want a bank accidentally losing a transaction. On the other hand, if you're dealing with big data, if your data structure is constantly changing, or if you need to scale out to millions of users quickly, a NoSQL database might be the way to go. It offers flexibility and scalability that can be hard to achieve with traditional relational systems. Many modern applications actually use both. They might use a relational database for core financial transactions and a NoSQL database for managing user profiles or activity feeds. Let's look at a real-world example. An e-commerce website. When you browse for a product, the product information, its name, price, and description, it's likely pulled from a relational database. The tables are well-defined. But what about the customer reviews? Or your browsing history that's used to generate personalized recommendations. That data can be messy and vast. It might be stored in a NoSQL database, which can easily handle all that unstructured text and user behavior data. When you finally make a purchase, the transaction itself, deducting the item from inventory and processing your payment, goes right back into the secure, reliable, relational data. It's a perfect example of using the right tool for the right task. The heart of database management is ensuring the data is accurate and reliable. This is often summarized by the acronym ACID, which stands for atomicity, consistency, isolation, and durability. Atomicity means that a transaction either happens completely or not at all. Imagine transferring money. You want the money to be withdrawn from one account and deposited into the other. If the system crashes after the withdrawal, but before the deposit, atomicity ensures the whole transaction is rolled back, so no money is lost. Consistency ensures that every transaction brings the database from one valid state to another. Isolation means that concurrent transactions don't interfere with each other. And durability means that once a transaction is committed, it stays committed, even if there's a power loss or system crash. Relational databases are champions of a CID compliance. NoSQL databases often take a slightly different approach, summarized by base, basically available, soft state, and eventual consistency. This means the system is always available, but the data might not be perfectly consistent across all nodes at all times. It will become consistent eventually. This trade-off allows for higher availability and scalability, which is crucial for many web-scale applications. It's okay if you see a new like on a photo a few seconds late, but it's not okay for a bank balance to be temporarily wrong. So, whether you're building the next big social media app, an online store, a scientific research platform, or just organizing your personal collection of books, understanding databases is crucial. They are the silent engines that power our information age, turning chaotic raw data into structured, meaningful knowledge. From the strict, reliable order of relational databases to the flexible, scalable power of NoSQL, these systems are fundamental to how we build and interact with technology every single day. The next time you refresh your feed or check your bank account online, take a moment to appreciate the incredible database working tirelessly behind the scenes to make it all possible. Thanks so much for watching. If you found this deep dive into databases interesting, be sure to hit that like button and subscribe for more content that demystifies the technology that shapes our world. Drop a comment below with any questions or topics you'd like to see next. See you in the next video.